Hello everybody and welcome back to our automaton regular and formal languages class. This is unit 8 in which we will discuss the concept and idea of regular expressions, and we will see what they are used for and how important they are in the theory of computation. And also what we will see later on is this very powerful concept that you may have encountered in your career so far, the concept called regular expressions and how powerful it is. And then we will formally prove that these are the same as finite automata, and the languages that these expressions describe are effectively that of a finite automata. So what do we call expressions? Basically, if you want to think about arithmetic expressions, when we combine a bunch of operations together, then we come up with something over the set of numbers that describes something, and for these we call them expressions. So for example, in an arithmetic calculation, we might combine the operations plus and multiply into a form such as the one you see here, and so this creates an arithmetic expression. And the arithmetic expression evaluates with the numbers and the operations that we have here into the number 32. 5 plus 3 is 8, and multiplying that by 4 gives us the number 32. So similarly, we can also use regular operations to build up expressions that describe languages, and these expressions, we call them regular expressions. An example of a regular expression would be something like this. If you combine a symbol 0 with the symbol 1 and symbol 0 in a combination of formats, then you will get the resulting calculation, or the resulting set. So as I said, and over the set of numbers, we use the plus operation and the multiply operation to build expressions. In the case of languages and regular languages, we use regular operations such as the union, such as the concatenation, such as the star, to build these more complex sets, or more complex languages that can be derived from the original. So a couple of notes about notations, of course, before we get to define regular expressions formally. When we write down a symbol in the alphabet, that symbol effectively evaluates to a singular set composed of the symbol. So when we write 0, then 0 basically is a kind of a shorthand notation for set 0. Same thing with symbol 1 and any other symbol. Also, when we concatenate symbols or languages or expressions, we can simply omit the concatenation circle. It's basically pretty much like when we multiply numbers. When we multiply, for example, 7 by n, we usually, as a shorthand notation, we write it as 7n, right? So basically, we do the same thing with the concatenation. So that being said, now you would realize, and you would see that when we union in the previous expression, the expression here, when we union 0 and 1, that doesn't make sense if you were just numbers. We can't union numbers. But if you think about those being shorthand for sets, then union 0 and 1 is effectively the same as unioning this, or making the union of set composed of a single element 0 and a set composed of single element 1, and the union of these two sets is going to be the set 0, 1. So if your alphabet was over the symbol 0 and 1, if your alphabet was composed of 0 and 1, then basically the union of the symbols in your alphabet will give you the alphabet. So what this means is that union of all symbols in your alphabet is equal to your alphabet itself. So so effectively, another way to talk about this expression is the shorthand expression for 0 set 0 unions with set 1, and then concatenating this set with a repeat of set 0 star. So what this means is that the language that this expression describes is effectively over the it starts with a symbol from the alphabet and it ends with any number of zeros at the end of it. So it could contain, so W could be 0, or it could be 1, or it could be 0 0, or it could be 1 0, or it could be 0 0 0. So this will be the 0 part of it, and this will be the 0 star part of it. Or it could be 1 0 0 0 0 0. This will be the 1 part of it. This will be the 0 star part of it. So this language that that the expression here describes is effectively a set of all the strings that start with any symbol from the alphabet, and the alphabet is 0 and 1, and end with 0 or more zeros. So why do we talk about regular expressions? Why is it an important concept here? Regular expressions actually have played a very, very important role in computer science applications, in a lot of applications that involve texts, and that you would require or need to sort of perform a search for a component in the strings that satisfies a certain pattern. You could basically look at the pattern and describe it, and then utilize an automated computational model to search your strings, your text for this component or for this pattern. And as such, if we could show that, and in fact we will later on show that these are effectively regular expressions and that they're basically effectively regular languages, we will be able to utilize this with a very finite and limited amount of memory, because then we can implement them with a finite state machine, and a finite state machine is, as we described, are the simplest kind of computational tools. In fact, regular expressions provide such powerful methods for describing patterns that utilities in Linux and modern programming languages such as Perl, .NET families of languages, and many text editors provide mechanisms for describing patterns with regular expressions. And so, for example, when you're looking at, for example, a date and time, you can specify the date and time to be formatted into a certain expression. When you're creating a text box, for example, in a web application, for the users to type in their email address, and you want to validate that email address, you could use regular expressions to make sure that this email address follows a certain pattern, such as a string concatenated with symbol @, and then another string, and then the dot, and then another string for an email address, and so on and so forth. So so these are very, very powerful tools in computing. So I've already talked a little bit about evaluating the regular expressions with the previous example, but let's look and see what does the value of the regular expression 0 union 1 and then the whole thing in parentheses star mean. If you remember from the previous slide, we said that 0 basically is nothing but just a shorthand for the set 0, and then 1 is the shorthand for set 1. So 0 union 1 effectively is when you take the singleton set composed of only element 0 and union that with the singleton set composed of element 1, and then you get the set 0, 1. And if your alphabet was over 0 and 1, then that would effectively be your sigma. So what does the star of this whole thing mean? It means that you're basically calculating the star of your alphabet. What this effectively is that the sigma star is any language that is a language basically that has any concatenations of any number of elements from your alphabet. So effectively sigma star is the set of all strings over the alphabet sigma. So for example, if your alphabet was the English letters, then sigma star would be any string that is composed of the English letters. If your alphabet was Roman letters, then it would be any string that can be made, whether they make sense or not, of the letters in the Greek or in the Roman alphabet. So let's take a look at 0 sigma star. What does 0 sigma star mean? Obviously, we said that sigma star is all the strings that can be made from the alphabets. So this will be all strings over sigma, which means that there's nothing really special about it. But if we concatenate it at the end of 0, then that means that now 0 sigma star is all strings that start with a 0. Right? So because 0 sigma star is still a string, if sigma star is any string, all strings from alphabet, if you add a 0 at the beginning of it, then effectively it's still a member of it will still be a member of that set. But by specifying that we want the beginning of our string to start with a 0, and then we don't care about the rest of it, we just put a sigma star. And that way, this expression will effectively evaluate to any string that you can think of and make with symbols in the alphabet that start with a 0. By the same token, this language made of sigma stars and 1, concatenated 1, is effectively all strings over alphabet sigma that end in a 1. Notice that it doesn't specify how many ones, because the sigma star a string from sigma star could be all 1s, it could be all 0s, it could be 0, 1, 0, 1, whatnot. So, so sigma star 1 basically gives us a set of strings that all of them have this concept, this thing in common, that whatever, doesn't matter whatever the beginning portion of it is, the last symbol of them all are the symbol 1. So how about if we just take these two expressions and unioning them with each other? So we know that then this first portion is the set of all strings such that W starts with 0, and then the second one, so that's the first one, and then the second one is all the W's such that W ends with a 1. And when you union these guys, basically it means that any member of the first set or member of the second set. So it would be the set W such that W starts with 0, starts, if I could spell start, that would help, right? So W starts with 0 or ends with 1. So that's how this second, rather the third language would look like. Now we haven't really talked about the intersection as an expression, but you could use intersection of these languages and they still be a member of a regular expression. But with keeping in line with the concepts and the definitions from the Cypser's book, we will limit ourselves with the concatenation, the star, and the union operations to build regular expressions. So before we go to formally define regular expressions, and let's talk a little bit about the precedence. Just like the arithmetic expressions and the mathematical expressions, certain operations may have precedence over certain other operations, in that when we're writing them in the expression, and it's the time for us to evaluate these, which one should we evaluate first? Because if you look at them, there's going to be there may be just a whole bunch of different operators that are involved, and so when you have the choice between choosing which operator to perform, the order of precedence becomes important. Just like the arithmetic operations, that the multiplication takes precedence over addition, and then the parentheses takes precedence over everything. The orders in regular expressions are defined as star having the highest priority, or the order of precedence, then followed by concatenation, followed by union. So if you have a choice of operations, for example, if you end up with a situation like this: A union B C star. So we have basically the three operations here. We have the union operation here. We have the concatenation operation here, and then we have the star operation here. Which ones should be performed first follows this precedence. So we basically take the star operation and perform it first. So basically this is going to be the one that's first applied. When that is calculated, then we are going to concatenate that with B, and so, or rather concatenate B with it, and then when that is calculated, then we're going to union this resulting set here with the first letter. So basically then what this means is that this basically calculates the union of the set B concatenated with the set C star. So this is, if I were to bisect this operation in terms of the order of precedence, this guy would be the first one to apply, this guy would be the second one to apply, and this guy would be the third one to apply. What if I first wanted to union A and B and then perform the concatenation and then the star? Then we use parentheses. So if I wanted the actual calculation to make this operation the first one, the concatenation the second one, and the star the third one, if I wanted this, then I would basically write this as A union B, and then concatenate that with C. And then if I have a bunch of parentheses, I could actually go to brackets and then star the whole thing. Actually, just to avoid confusion, let's make these big parentheses. So all of these things are parentheses. So with parentheses now, this one, the union will be performed first, the concatenation would be performed the second, and then the star will be performed the third. So without concatenation, the operations go from right to left. With parentheses, without parentheses, the operations go from right to left. With parentheses, the operations go from left to right, and that is because the parentheses would take the precedence, and in fact the innermost parentheses would take the highest precedence. And parenthesizing and disambiguating things would require a higher level of capability that regular expressions and regular operations don't have. For those, we get into pushdown automata and context-free languages. But besides that point, here's the way that we define the precedence of our operations. So now that we talked about these things and we saw a little example of how these operations are performed, what is the formal definition of regular languages? How do we formally define a regular expression? Formally, and this is definition 1.52, definition of regular expression, we say that the expression R is a regular expression if R is one of the following. If R is a symbol A for some symbol in the alphabet, so any single letter of the alphabet by definition is a regular expression. Also, the lack of any symbol in the alphabet will be also a regular expression because it evaluates into the empty symbol or the empty string. So the epsilon symbol epsilon is also a regular expression by definition. By definition, the empty set is also a regular expression. So basically, it's a set that is made of no strings. It's empty. Since the operation union is a regular operation, performing union over two regular expressions results into a regular expression. So if you have regular expression r sub 1 and r sub 2, if you union those two regular expressions, you would get a regular expression. Same thing with concatenation. If you have r sub 1 and r sub 2 being regular expressions, then the concatenations of the two will be also regular. And if you have a regular expression r sub 1, the start of that expression is going to be a regular expression as well. Now, one of the things that you might want to ask yourself and kind of be a little bit pessimistic about this definition is that doesn't this definition put us in danger of defining a notation of regular languages recursively, or rather circularly? That would be true under one circumstance, and that would be if the expressions that are defined by the union and concatenation in the star operation would be either smaller than or equal to the original expressions. So that would put us in danger of circular definition and make our definition invalid. However, if you look at this definition of regular expressions, you would see that the first basic components of something being regular is one element objects. So either no element, empty set, one element, empty string, epsilon, or one element, one symbol, letter. When you have these one element letters, effectively, if you want to think about this, this is like our base case for our induction, right? And then when we combine these guys with the union, the concatenation, and the star operations here, we would see that we start with a smaller language, r sub 1, r sub 2, that initially would be either one of these three, and then we combine these two with union and concatenation to build bigger languages, and then we combine those languages or those expressions with union and concatenation to make bigger expressions and bigger expressions and bigger expressions. This is an example of inductive definition, and the definition of our regular languages, regular expressions here is effectively an inductive definition, in that r sub 1 and r sub 2, the components that we are using in the union part, concatenation part of our and concatenation part of our regular expression definition are always smaller than r, the combined version of the two. So basically, we are effectively defining regular languages, regular expressions, in terms of smaller regular expressions, not circularly. So we might omit parentheses also in our regular expressions if there wouldn't be any ambiguity in the expression. So for example, if we say r sub 1 concatenation with r sub 2, we could write it like that, or we could write it just r sub 1 concatenating with r sub 2. So this would not really define create any certain ambiguity in this definition. So if we don't need parentheses, we may omit them. Now, we define the star operation, and the star operation basically gives us a really neat way of defining and building up regular expressions that are in the form of any repetitions of a certain kind of string, um, which includes 0 repetitions. So we also, for convenience, are going to define the plus operation, and the plus operation is effectively the shorthand for R concatenated with R star, meaning that the language that it creates over expression R is going to be the set of all the strings that have 1 repetition or more repetitions of all strings from R, whereas the R star could also possibly make 0 repetitions or have empty string as a component. And the relationship between the R star and R is that and R plus is that R plus is effectively R star, and R star is effectively R plus union with the empty string or 0 repetitions of strings from the expression R. So one thing that we can also distinguish between regular expressions and the regular languages they describe is to write the language of the expression, L of R, and then this we call it language of regular expression R. So R from this point on is a regular expression, and L of R is the language of that expression. And this is how we disambiguate the languages, regular languages that are expressed by a regular expression and the regular expression itself. And again, if you remember, regular expression is just an expression, which is a bunch of sets and the operations over those sets, and regular languages are effectively the sets of strings that satisfy the properties of being regular, meaning that some NFA or DFA recognizes them or accepts them. So let's take a look at a couple of examples and see how some certain regular expressions evaluate. So for all of these examples, the alphabet is effectively the set of symbols 0 and 1. So the first regular expression, top left, is 0 star 1 0 star. So if you look at this, star basically means like every possible repetitions, every possible ways that that set can be created. So 0 star is the set of 0 or more zeros. So 0 zeros is empty string, 1 zeros is just 0, 2 zeros is 0 0, 3 zeros is 0 0 0, and so on and so forth. So for this string, if you look at the strings that are in the form of this regular expression, they may start with any number of zeros, they may end with any number of zeros, but they must have exactly 1 and 1 1. So 0 star 1 0 is the set of all the symbols to strings that W has 1 and only 1 1. Contains a single 1. Now how about this guy here? Sigma star 1 sigma star. If you look at this and just try to find the difference between this expression, the second expression, sigma star 1 sigma star, and the first expression, 0 star 1 0 star, you notice that in the first expression we have limited what the language, what the symbol can start with, which is basically any number of zeros, and what it can end with, any number of zeros, and therefore there's only one in it, and the beginning of it is going to be a bunch of zeros, and the end of it is going to be a bunch of zeros. With the second expression, though, sigma star effectively means any number of strings that can be generated from the set 0 and 1. So it could be any substring. So the beginning of this letter can have any number of zeros or ones, and the end of this string could have any numbers of zeros and ones. But the middle section is also exactly 1 1, which means that the beginning part of the strings may have ones, may have some ones, and the same thing with the end of the string. So this W is going to be the set of all the strings W, such that W has at least 1 1. Whereas the first symbol here, the first expression, specifies that there should be no ones in the beginning or no ones in the end of the string. That basically limits the number of ones to 1, a single one. In the second expression here, I may have some ones in the beginning, I may have some ones in the end of the string, I may have no ones for that matter, but I do have specifically exactly a single one. And I may have more ones here, so it could be 0 1 0 1 0 1, and it could be 1 0 1 0 1 1, but it will have this one is guaranteed to have. So I may have, so these strings will have more than one, at least one symbol one. Let's put it that way. Yeah, just it's a mouthful. How about this string, sigma star 0 0 1 sigma star? What kind of strings W's does this expression create? Same thing with the above expression, in that the beginning of the string could be any string. So for the beginning of the string, we don't care whatever the beginning of the string is. It could be empty string. It could be a whole lot of different kinds of an infinite amount of combinations of the letters from alphabet. Same thing with the end of it. But the middle section of this string is basically effectively limited to being 0 1 0. So if you think about this as a substring, then what this expression specifies is that this expression is evaluated into any string such that W contains 0 0 1 as a substring. Okay, so as substring means that it can be just 0 0 1. So the string 0 0 1 contains 0 0 1 as a substring. This 0 0 1 could be at the end, 0 0 1 could be at the beginning, or 0 0 1 could be anywhere in the middle. And this flexibility is given by the star of sigma operations. Star operations of sigmas here. Let's get a little bit more complicated. How about this guy? What kind of strings does this expression recognize? Well, if you look at the middle section of this string, it specifies that here, if you have a 0, then that 0 must be followed by at least a 1. So it could be 0 1, or it could be 0 1 1, or it could be 0 1 1 1, or whatever. But this has to be in the format of every 0 must be followed by at least a 1, and then we're going to basically star this operation, which means that then when you do this star, then this could transform into 0 1 0 1 or 0 1 0 1 0 1, or any kind of repetitions of that. Same here. So 0 0 1, I mean 0 1 1 could be into 0 1 1 0 1 1, or 0 1 1 0 1 1 0 1 1. So any repetitions of that. And then the beginning of your string could have any number of ones. So there's only one limitation, in that there will be no multiples of zeros consecutively in this language, because the one star at the beginning of this expression limits that, and that your string, if it has a 0, that 0 will be followed by at least a 1. So this set of the expression, the fourth expression here, is the set of all the strings such that every 0 in W is followed by at least one 1. So it could be more than 1 1. Okay, so that's how you specify a certain condition for like symbols following each other. So how about this fifth language? What kind of strings does this language recognize? This language basically recognizes the strings that are effectively twice repeated of the same string from over sigma. So for example, if sigma is 0 and 1, and then you concatenate that with 0 and 1, right? So here you've got the set 0 and 1 that you can draw from, and then so you draw one symbol from set 0, 1, and then you concatenate it with one symbol from set 0 and 1. When you do this, then effectively you have two symbols, and then you repeat that any number of times you need. So this effectively means all the W's that actually it would be a set of strings W's such that W has even length. Okay, because each of these sigmas represent just one symbol of your alphabet. So it could be 0 and then 1, or it could be 1 and then 1, or 1 and then 0, or 0 and then 0, and then it could be any repetitions of this. So it could be 0 1 0 1, or it could be 1 1 1 1, or 1 1 1 1 1 1. So any repetitions of symbols that are like any repetition of a string with two symbols in it is going to have multiples of 2's. How about this the last one? This is also fairly easy. So you probably guessed already that this strings in the language sigma 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 star have lengths equal to 3k, or multiples of 3, because this could be 0 or 1, this could be 0 or 1, this could be 0 or 1. So you basically pick a 0 or 1 and then concatenate it with a 0 or 1 and then concatenate it with a 0 or 1, and then you can repeat that any number of times you want, which basically makes your strings to be multiples of 3's in terms of their lengths. How about 0 1 U 1 0? So this, what I will do is that I will basically make this into a language, a string. So it's going to be string 0 1, string 0 1. So it would be 0 1 union with 0 1. I mean 1 0. And then when you union these two, you're going to get 0 1 comma 1 0. So it's going to be a set of 0 1 or 1 0. There is basically two symbol strings, 0 1 or 1 0. Let's get this a little bit more complicated. Let's look at this expression. So this expression may sound a bit scary, but if you wanted to kind of make sense of these things, I would suggest you basically, when you see unions like this, you put a kind of sort of brackets, pseudo brackets for the things that are separated by the unions, and then you would realize that this is effectively union of 4 different kinds of sets. So what are these 4 sets? The set 1, I'm actually going from the end to the beginning, union with the set 0, union with the set 1 sigma star 1, union with the set 0 sigma star 0. Okay, so remember here with sigma star 1, actually it's kind of sort of the opposite of it. We said that if you do sigma star 1 sigma star, that means that you've got at least 1 1 in the middle. In this case, here I have a 1 in the beginning and a 1 in the end, and then any number of repetitions of the strings in the middle. I have a 0 at the beginning, a 0 at the end, and then any number of repetitions of strings there. Okay, and then this is basically just a single 0, and this is basically just a single 1. So if you wanted to format this into a formal definition, then it would be the strings of the set of all the strings such that W starts and ends in the same symbol, right? So if it has only one symbol 1, it starts and ends with the same symbol. If it has only symbol 0, it starts and ends with the same symbol. If it starts with 1, it ends with 1. If it starts with 0, it ends with 0. Union all these different sets, and we get the set that we were asking for. So let's take a look at this one then here. 0 union with the empty string, and then concatenation of 1 star. Basically, if you look at this, this could be the concatenation of 0 and 1 star, and then union of just 1 star. Because what this means is that this concatenation, the second part of this concatenation is just 1 star, but the first part of this concatenation would be either epsilon or the set 0, right? So which means that in this case, this language is equivalent to the union of either if you have 1 star, any number of repetitions of 1s, or a 0 and then followed by any numbers of 1s. So it's basically the union of these two operations. So how about 0 union with epsilon and 1 union with epsilon? So if I wanted to write this down, I would say, well then, this first portion is the set 0 epsilon, right? Because it would be the union of epsilon, union of with the singleton set 0, and then concatenating that with the set 1 comma epsilon. So when we do this, then it would be either, so you concatenate the first element with the second element from the first element from the second set, so that gives you 0 and 1. And then concatenating epsilon before 1 gives you a 1. And then concatenating 0 with epsilon gives you a 0. And then concatenating epsilon and epsilon gives you epsilon. So this is a 4-member set, and it would be either 0, epsilon, 1, or 0, 1. So this is the set here. What happens if we concatenate empty set with 1 star? We haven't talked about it yet, but this is sort of kind of like by definition. If you concatenate the empty set with any other set, you would get the empty set. Kind of counterintuitive, but concatenating the empty set to any set will give you the empty set. So 1 star concatenation with the phi operation will give you phi. It's basically practically like multiplying things by 0. If you multiply 7 by 0, 1000 by 0, a billion by 0, you get 0. If you concatenate any set with the empty set, you would get, so basically it nulls it. It would give you the empty set. However, the star pot operation on the empty set, you might think that this is a concatenation of the empty set with itself, which is kind of sort of true. So why is it not empty? Actually, let me just tell you this. It's the set epsilon. So star of the empty set is epsilon. It's not empty set. It might also sound a little bit counterintuitive. You might say, wait, well, isn't this phi? Isn't it phi concatenated with phi concatenated with phi? So isn't it kind of like concatenating phi with itself, or the empty set with itself, a number of times, and each of these are empty sets, so the union of all those should be empty sets? That is true. However, the 0 concatenation of phi with itself is what gives you the epsilon, right? So if you think about this basically also is sort of like raising something to the power 0, which is 1. So epsilon is kind of sort of like that. The star operation of the empty set, as it is with the star operation of anything, if you have a set A and then you star that, that would be equal to epsilon and any concatenation of strings from A. Okay, so this is basically, epsilon is a member of the star set. So concatenating or starring the empty set will give you one single set, singleton, and it's called the empty set, epsilon. Alright, let's talk a little bit about identities and describe and see what happens with the identity of the union and the identity of the concatenation operation. Because remember, we said that the regular expressions are effectively made of simple regular expressions or regular operations on those expressions, such as union or such as concatenation or such as the star operation. So the union will have an identity function or an identity set, and the identity set of union is phi, which means that if you union any expression with the empty set, you would get that expression itself. Remember the fact that the concatenation of phi with any set would give you the empty set, or the empty expression, or the empty language for that matter. So the identity element for concatenation is epsilon. If you concatenate epsilon with R, and it's actually it's a symmetric operation also, or concatenating epsilon at the beginning of R. Actually, let me just make this a bit more obvious here. So concatenating epsilon and R will give you R itself. And also remember, if you're not careful and you union the empty string with R, you would get a language that is made of the symbols of strings in R, comma, epsilon. Right? So if epsilon is not in your language and you union it with epsilon, then you would effectively erroneously are adding epsilon to your language. So you should be kind of careful about when you're dealing with identities, and these are your pointers here. The identity of union is phi, and the identity of the concatenation is epsilon. However, the epsilon with union is not going to always resolve in R. Same thing with concatenating phi with R. Will not yield R. Okay. Now, this is an example of how regular expressions are useful. Let's say that if you have a set D, and D is the set of digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's say we call the set S to be the set of symbols that we could operate on, and these symbols are dot and plus and minus. Okay, or period for the decimal point, plus for the plus sign, and minus for the negative sign. Then what we can do is, if we wanted to specify a floating point number, and so obviously if you have programmed at all, you would notice that you can program numbers like 32, 3.1, 7 point, just for it to represent a decimal number, and then negative 0.54, and so on and so forth. You can write these numbers like that. and then your compiler will be able to automatically recognize what these things even mean, right? So 32 would be an integer, 3.1 would be a float operation, plus 7 point, and then followed by nothing will be a floating point number also, positive, and then same thing with negatives. And you may represent negative 0.54 with also negative 0.054 or negative 0.000.54, right? Or negative 0.54, and so on and so forth. Same thing here. You could do 7.0 or plus 7.0 or plus 7.0000, and so on and so forth. So how does this represent? How does it compute and your expression evaluated? So the regular expression that specifies all these things and that your compilers can recognize them and find out what they are is composed of a very simple regular expression that is the concatenation of two parts. The first part will be the part that specifies whether your number is a positive number, a negative number, or that you don't want to specify a sign for it. And then if you so the first part concatenates this part, that part, and that part. These parts are coming from this section, and then you concatenate it with any number of different kinds of ways that you want to specify the digits, right? So this is also a 4-part option here, actually 3-part, that, and that. So the first part is at least 1 digit. Okay, so it could be 3, could be 5, it could be 7, it could be 75, it could be 32. So this part is the set of at least 1-digit numbers. And then you union that with the second part. So this guy, what is this guy? This guy is at least 1 digit followed by a period followed by 0 or more digits, right? So at least 1 digit here, so you could put like 7 and then a period and then 0 or more numbers. So you could put 0 point, 7.1, 7.300, 7.001, 0137, and whatnot. And this could be at least 1 digit, so it could be 127.00 and stuff like that. So this is the point, at least 1 digit before it and 0 or more digits after it. So that's this section. And then how about this guy? What does this guy represent? This guy represents 0 or more digits and then a period and then at least 1 digit, right? So this could be 0 or more digits, so it could be 0 digits and then a period and then 1 or more digits, so 0.1, 0. Or 0.752 and stuff like that. And then it could be more than 0 digits here, so it could be 1.372 and so on and so forth. So effectively then the whole expression evaluates and can actually take care of any combinations of positive or negative or without any sign, integers or decimal numbers in any format that you could think about. You could represent that with this regular expression, and this regular expression can be evaluated. And that's practically the power of these regular expressions. The reason that we're studying these things is that they're quite powerful, and in computing and in computer science applications, they have a lot of applications. Parsers and a whole bunch of different technologies that basically evaluate these regular expressions are a very important and fundamental component of compilers and so forth. However, there is a limitation to these expressions, and we see that why we need more advanced computational tools to be able to do more advanced things that we want. But at least with this example, you should exactly see how powerful regular expressions can be in terms of their descriptive power, that they can describe a very complicated set of kinds of languages. But then again, these are regular expressions, so they express and describe sets of regular languages. In fact, all these representations of numbers that I talked about is effectively a regular language. So this is our basic overview and going over the regular expressions and what they mean, how they how they can be evaluated. And next, we would go ahead and spend the rest of this unit over studying the equivalence of regular expressions in finite automata. So that will be next.